Thank you. Hello, everyone. Good afternoon, and thank you for coming to the talk today. So it's my great pleasure to introduce Megan Hofmann. She's a PhD candidate at the Human Computer Interaction Institute at Carnegie Mellon University, advised by Scott Hudson and Jennifer Manko. She's a Zero Flow and an SF Flow and a Center for Machine Learning and Health Flow. So she served as the Accessibility Chair for UISD from 2019 till 20, and is a member of the Program Committee for UISD during 2021 and 2022, as well as Assets in 2022. So she's been active in the HCI-related conferences with a lot of publications, and her work on emerging area of medical making has won actually multiple awards at ACM CHI conference and Assets. So in fall 2021, she developed and taught a new graduate special topic course on machine learning at the Paul Allen School of Computer Science at University of Washington. Thank you for coming today, and please.
Thank you. All right, I'm excited to get started. So today I'm going to be talking to you all about my work in the space of optimizing medical making. I'm going to give you kind of a little bit of context for the relationship between healthcare and digital fabrication and the types of systems I work on in that space. But first, I want to talk a little bit about how I got into digital fabrication research. This is the study of design tools and computer-aided design tools that facilitate using machines like 3D printers or laser cutters or machine knitting. And I really got into this because, to me, digital fabrication promises us that anyone can design and make just about anything. The tools that we have to support this kind of activities have come a really long way over the decades, pulling from many spaces, from graphics, machine learning, and human-computer interaction. But a lot of these interfaces are still targeted at a small subset of users. They're really thinking about affording kind of the techniques relating to engineering and other types of technical expertise. So it's better perhaps to say at the moment that digital fabrication is really about engineering and supporting engineers in making all of these interesting devices. My work instead is more focused on building domain-specific tools so that we can target different communities who have different types of expertise. In the digital fabrication research community, there's a lot of work on domain-specific tools, largely targeted on supporting more technical experts, looking at kind of specific areas of fabrication. And to a lesser extent, there's work on supporting novice communities and doing things like creating tactile graphics for people who are blind or have low vision, or creating personalized casts with clinical applications. But the problem I have with a lot of the work focused on these so-called novices is that they think of them as having no expertise because they have none of the technical expertise to use these tools. Instead, I like to think of them as orthogonal experts, people who have some kind of expertise that is separate from the domain-specific engineers and expertise to use these tools, but still have some expertise that is really critical to problem solving in their domain. To build those domain-specific computer-aided design tools, what we really need to do is bring these communities together, take orthogonal experts from a variety of different places and merge them with people who have this technical expertise and have a tool be the kind of medium between those two. But we all know how to build tools and we know exactly how hard it is to do that. So building one for each interesting domain would essentially be impossible. And so instead I focus on what I call meta tools, the tools that help us bridge these communities together and build tools much more rapidly. Meta tools are systems that help us implement tools by leveraging domain expertise. So some of the work that I'm going to talk to you about today is looking at using meta tools to support new domains like tactile graphic design, automatic splinting and occupational therapy, the design of PPE for fighting the pandemic, and then also my little dabblings in the space of machine knitting. And the reason I want to talk about these different domains is because they support different types of users who I consider those orthogonal experts, people with disabilities, professional caregivers, clinicians, and craft communities. Before I talk about those systems, I want to talk a little bit about medical making itself and my exploratory work in this space, talking about how we kind of work deeply with these communities and to build a kind of bottom-up perspective of what the types of tools they need are. Medical making is a relatively new field, and it's the application of digital fabrication technology to the design of medical devices and applications at the point of care. I've been working with different communities in this space for many years now, looking at kind of the major communities who have been doing 3D printing work in particular in healthcare settings. I got started by working with occupational therapists, a school for children with disabilities, to work on things like building mobility grips that are customized to their particular gripping patterns. This work evolved, sorry, the math keeps slipping down a little bit. This work evolved into more work focused on prosthetic devices, and in particular, supporting people with limb difference in designing the end effectors of their own prosthetics. So young 9-year-old Wilbur here could design a holder for a cello bow so that he could use his prosthetic device to play the cello in his school's recital. Over time, this work has started to transition more into kind of core clinical spaces. I started working with folks like Beth Ripley, pictured here at the Seattle VA. She's a radiologist who uses 3D printing to print models of what she sees in her imaging so that she can communicate better with surgeons and other clinicians as well as patients about what she's seeing and what is going to be the treatment process to go through. In contrast, I've also worked with people like Dr. Tareq Libani here, who's an emergency medicine doctor in Gaza, and he uses 3D printing instead to create common medical devices like stethoscopes, and now really a focus on PPE, to meet the needs of the failing supply chains in Gaza in response to the medical device embargo there, as well as the current supply chain crisis caused by COVID-19. Along with all of this work, there's been a surging interest in supporting fabrication in healthcare, particularly coming down from the NIH with the invention of the 3D Print Exchange. This is an online repository that anyone can submit a device to, and then that device can be shared with the global community to use for 3D printing in educational settings as well as in healthcare settings. One of the main challenges of the NIH design, though, was that it's really just an open repository. You submit to it and it kind of goes into a black hole. But a lot of the clinicians that we were working with who were trying to adopt these technologies wanted to know whether or not a device was safe or effective. They wanted to know what the review process was to go through it. They were looking for something similar to FDA approval, but that just doesn't exist for these open repositories. We ended up building a set of recommendations for what this review system would look like to meet the demand of the exchange. And I'll talk a little bit more about how that came forward in just a second. But we kind of thought we had come to an end of looking at these communities, at least for a little while back in 2019. I was about to take a break from this research, and then COVID happens. And seemingly overnight, we go from a few thousand people worldwide doing this kind of work to hundreds of thousands of people printing PPE in response to the pandemic. The community I work most closely with during the pandemic is actually a Colorado-based community. This is Make for COVID. I was quarantining down in Denver with my mother when everything started, and I see my high school engineering teacher's daughter show up on the local news. So I give him a call and see if I can get involved in their community in some way. And then they ended up staying there for about 6 months as an organizer. This community ended up producing over 100,000 pieces of PPE. If you've been in a clinic during that period of time, you might have even seen the face shields that were being used. And they ended up distributing them across all of Colorado. They built this remarkable supply chain. They were working with the Civilian Air Patrol to bring these things to the rural regions of Colorado so that they could maintain a consistent supply. But they ended up facing a lot of the same challenges we had seen with the smaller communities before the pandemic. They were really concerned about verifying their devices and making sure they were safe and effective, particularly when they didn't really know how they were going to be used or how long they were going to be used in a clinical setting. We had no idea in 2020 when the supply chain would start back up again. And a lot of the designs that came from this kind of maker community, once we looked at them or inspected them for a little while, they would break down in some way, right? It would come out perfect and then you play with it for a little while and it bends or breaks in some way that could be really dangerous if someone's using this in a clinical environment. And so we had to build a quality control protocol at the warehouses in Denver that was really a bottleneck for a lot of this work. I think it ultimately limited their ability to scale beyond Colorado to other regions. Now, the NIH was trying to solve this problem at the exact same time because they were receiving all of these different designs specific for COVID-19. And so they took this as an opportunity to release a review process that was based off of our set of recommendations. They got a set of about 100 reviewers nationwide from within the NIH, the American Makes, which is a DoD group, and the VA to review all these designs as they came in. And they would decide whether or not things were fit for clinical use. This means that they were safe in a medical environment, whether they're fit for community use, which means probably shouldn't use them in a clinical environment, but they're probably safe. And then finally, they would mark some designs as being completely unsafe, not fit for use, things like ventilator parts that just were not being made out of the right materials. Problem was, even with this review process, with the surge of COVID-19, they just couldn't keep up with the process. There was no automation. And so you can kind of imagine this as like your local conference having about a few thousand more papers than last year submitted to a review process. It's just going to be impossible to get through all of them in an even equitable and meaningful way. Since then, we've done a review of the designs that were reviewed on the NIH 3D Printing Exchange, and we found something very interesting. The communities that worked with clinicians specifically in these design teams were much more successful at getting clinical designs over the communities that didn't have them. Unfortunately, the majority of teams did not include a clinician. They had no access to this clinical domain expertise. And so we really were missing out on an opportunity to include clinicians and produce more advanced devices. I've kind of bucketed three main limitations that I've focused on over the last few years from this work with these medical making communities. The first one is a material limitation. A lot of these clinicians want to work with deformable materials, things that flex and shape to the body that can go inside the body in a meaningful way. But the design tools that we have out there are really focused on things like 3D printing with hard plastics or working with different types of hard materials. And so the affordances are completely different and the chains that exist for it just don't work. The next challenge is with reuse, and this is really in particular to things like the NIH 3D Print Exchange. A lot of these communities want to just pick up a design and reuse it, modify it in some small way, and then apply it in their practice. But they have no way of knowing if these meet verification standards or if they're safe to use if they make those modifications. And we can't possibly rely on human reviewers to make these decisions at scale. And then finally, some of the clinical communities we worked with, particularly groups like occupational therapists, really wanted design to be something that happens in a few minutes in an appointment with a patient, something that can automatically fit something to a patient, rather than a design iterative process that may happen over months or weeks or years. And so we really need to focus on building tools that support these very small types of customization, rather than general purpose tools in this space. And with that, I want to talk about three different systems that I've built in response to some of these challenges. The first one is called Nitpick, and it's focusing on building a pipeline for machine knitting, thinking of textiles as this new space to explore deformable materials. Next project is called Parts, and it's about improving 3D model reuse by applying software engineering principles to the 3D modeling domain. And then finally, I'm going to talk about my most recent work with Optimum, which is a Meta-Heuristic programming toolkit, which makes it easier for us to rapidly build generative design tools that would fit into these kind of short-term clinical design processes. Let's start off with Nitpick. It's kind of ironic jumping into machine knitting as a digital fabrication space. These are very robust machines. I would hazard a guess that every single one of us is wearing something that was made on one of these machines. They're on factory floors across the planet, but the design tools to work with them are not much better than assembly programming. I mean, we are really talking about like individual instructions for every single design that you produce. Despite this, there's lots of already existing interesting medical applications, everything from the design of particular materials for the orthotics that you might find at the local drugstore, up to the knitted splints that you can put inside of your body. And the reason knitting is used in these applications is because knitting, unlike other types of textiles, has highly controllable physical properties that are independent of the yarn material that you're making these knitted structures up with. You can make things that stretch in interesting ways or curl up on themselves or have engineered opacity into them. And better yet, all of the expertise we need to do that type of engineering already exists in crafting communities across the world, because these are the same properties that they use to create different types of aesthetic textures in a hat or a scarf or a sweater. And so all what we really need is a bridge between these orthogonal experts from craft communities into the engineering space that has access to these machines. This is how immature the current platforms are. So this is AutoKnit. This is a Shimaseki software for their industrial knitting machines. That's about 50% of the global market. And here, each pixel represents an instruction to be run at a specific time in the program. There's no parameters, there's no repetition of these structures. It's very, very difficult to work with. So in this case, this will produce a fingerless glove, but you can imagine taking that texture and putting it onto a sweater would require completely rebuilding the system. Hand knitters have come up with a little bit of a better approach. They write a language called KnitSpeak, and they developed it themselves. This is a program-like structure that they use to follow the instructions for hand knitting. And it has things like loops and parameters and all of these different structures that make it just a little bit easier to build a complex texture. We built a data set from a book of hand knitting patterns, as well as an online open repository called Stitch Maps of all of these different textures. And then we built a compiler from it to a language called KnitOut, which is an assembly language for our knitting machine, so that we could output these different designs and work with them. The important part here is that we need some kind of intermediary structure, which will actually let us kind of build off of these and combine them in interesting ways. But to build that intermediary structure, we have to learn from hand knitters exactly what that structure of knitting is. So knitting is built on the principle that you pull loops of yarn through other loops of yarn. You can imagine having this white loop here. If you're ever to pull on it, it would just kind of come taut. If you pull a gray loop through it and then pull on that white loop again, it will be stabilized. You can then build a grid-like structure of all of these loops pulled through loops. That's how you make fabric. And we can represent this as a graph structure where we have loops representing nodes, edges along the yarn, these green edges that are going side to side, and then stitch edges where we pull a loop through another loop along those purple up and down edges. And once we have this knit graph structure, we have a full compiler. We can now start generating different designs for the machine. But we can also go backwards. We can use a virtual machine from the assembly language to go back to knit graphs, and we can use program synthesis to go to the hand knitting patterns so that we can quickly prototype on them without access to the machine. And because knit graphs are such a flexible structure, we can start to build design tools on top of them. We can start to think about things like simulation of these materials, figuring out different material properties, or designing them and combining them in some interesting way. For example, we developed a set of formulas for predicting some of the key properties in the knitting space. In particular, I'm going to talk about curl, which is the ability of a fabric to kind of curl up on itself. The way this happens is that if you pull a loop from one direction, it's going to curl forward or towards you. If you pull it the other direction, it's going to curl away. You can then measure the effect of curl descending from that original loop in a recursive way to figure out how much each one is impacting the bottom of the fabric. And you can take the average over a region of a subgraph to predict how much that section is going to curl up on itself. In the class I taught last fall at the University of Washington, we gave students an opportunity to build this pipeline for themselves, and then gave them 4 weeks to figure out how to build a design tool for some aspect of knitting that was interesting to them. If folks want to check this out in person, I've got some samples from that class to play with afterwards. They were looking at all sorts of things from color work to different types of 3D modeling techniques, as well as looking at the application of playing with the stability of these structures as almost a programming language and verification problem. It was really an interesting class to start to build different tools that looked at deformable materials in a new way. The reason I focus on textiles in particular is because these deformable materials support body compliant design. This is critical for building things like garments and different types of wearable technologies, but it also gives us a new platform to think about medical making in the space of things that might go inside the body or attach to the body for some medical purpose. Now that we have a platform for reusing the designs that knitters produce, and we already have existing platforms for accessing 3D models from wider communities, it's important to think about what happens to these materials as they go out to a global community. Our goal here is really to think about reuse as a way of amplifying expert-made designs. The designs that have gone through a lot of review process are known to work very effectively. So for example, in the space of printing face shields, we might want something with a splatter visor that protects you from droplets from above, or a design that's known to be highly durable and comfortable over a long period of time, or one that's really quick to print and reliable on kind of cheaper consumer printers that could be accessible to the wider community. When we look at the designs that were submitted to the NIH 3D Print Exchange, we see this pattern of reuse where there was this huge surge in submissions that got reviewed for clinical use. And then a lot of remixing where people were just making tiny changes on these designs and slowly that dropped off very rapidly over the next 6 months. These remixing patterns were often very simple things like changing out a material to use whatever they had available to them, adjusting the size so it fits different body types, or adding a component like that splatter visor onto a preferable design. These are the kind of things that should be relatively easy. They're small changes, they shouldn't require that much work. And yet we find that the modifications are very difficult. In many cases, people completely rebuilt the 3D model from scratch just to make a small change, like what a parameter for sizing would be. Now, of course, from software engineering, we know a lot about how to reuse designs, in particular, how to reuse code and modify it to serve some new type of purpose, right? We do things like we encapsulate our code by its specific purpose. We separate different concerns. This will help us test different pieces of the system independently. And we relate properties to methods of modifying them so that we have specific rules about how things can and cannot be modified. The core component of parts is this idea of functional geometry, where we take pieces of geometry like a 3D model or a sketch, and we associate it with a simple script for doing the same kinds of coding tasks that we would normally do. By having functional geometry, we can encapsulate geometry by real-world purpose. We can associate geometry with automatic tests, and we can relate geometry to rules for modifying it. So for example, let's say we're going to build a cup holder that attaches to your bike handlebar. You want to be able to assert that we reserve space for both the handlebar and the cup, and that those two pieces of geometry should not intersect with one another, even though we're not going to 3D print either of them. Or we can integrate geometry together. We can say, I have a cup holder and I have this mount, I want them to go together. And we can use code to generate that blue vine-like structure that goes between the two of them. With parts, we built up a library of different 3D modeling design patterns based off of design patterns we found in a study of Thingiverse, which is a general purpose 3D printing repository. We looked at about 1,000 different designs that all connected to real world objects and looked at the ways that designers were going through the process of kind of incorporating these objects that were not going to be fabricated. We then gave this to a small group of users, and we gave them 2 tasks over 45 minutes each. They could either reuse existing geometry in a standardized tool, or they reuse geometry from our toolkit. And what we asked them to do was to build that cup bike handlebar. And we broke this into about 6 different tasks. With the standardized tool, no one was completely successful in finishing all of the tasks, and it was kind of random which tasks they were successful in. They didn't really have any guidance of how to manipulate these different geometries and combine them. With the functional geometry component, they were all capable of doing the first 4 subtasks, and then they were able to do 2 people were able to do the last 2. And this was in a very short amount of time for a 3D modeling task, particularly in a tool that they had not encountered before. I want to give a more concrete example of what functional geometry will look like and how it supports reuse. This is a model that I found during that study on Thingiverse. This was what I really wanted to create. It was this kind of CD disco ball lamp thing. But all they gave us was this geometry that I couldn't really figure out how it went with the different components. And I know I'm not the only one who struggled with this today. The only comment on this was, oh, come on, how do we put this together? So we rebuilt our own piece of it, and we built this lamp where you can see the 3D model much more accurately reflects the final design. But I want to draw particular attention to that red bubble at the center. This doesn't just represent the light bulb, it represents heat coming off the light bulb. Our first prototype actually started to deform over time because the incandescent bulb was melting the plastic. And so we needed to put an assertion around it that says, you can't put anything 3D printed in this space. This gives us a very easy mechanism for kind of embedding design requirements into the 3D model in a way that someone else could come along and pick it up, see that that assertion is violated, and then know that that's the existing requirement. If we want to think about this in a space like facial design, we might have an assertion that asserts that there is space between our forehead and the face shield. This ensures that there's airflow and it doesn't fog up. We want to have things that an integrator that affects different parameters around fit to the temple, so we can adjust this to different bodies. And we want to adjust the back end to different types of compliance requirements because the different strap materials are going to affect that fit. From software engineering principles, we know that reusable designs are going to be modular. Ultimately, they need to be verifiable. And ideally, they need some support for automatic adaptation. And this is probably less important in the space of kind of the trinkets that we see on something like Thingiverse. But it is no exaggeration to say that it is a matter of life or death in a space like the NIH3 Prey Exchange, where creating a design in the wrong way or modifying it in the wrong way would be the difference between saving a life and ending one. My goal is to increase design reusability because I think this will make the repositories like the NIH 3D Print Exchange ultimately more useful to communities who don't have the technical expertise to create models from scratch, but still want to adopt them in their practice. Of course, there are applications where a small modification to an existing 3D model is just not going to be enough to solve the problem. And in that case, we need to look at things like generative design as a solution. So this is my last project, Optimum, the optimization programming toolkit integrating meta-heuristic methods. And it's focused on supporting generative design, which is an inverse operation or an inverse design process where the user provides a set of goals into an optimization workflow, and that will produce an automatically generated design that will satisfy their requirements in some way. There's lots of successful examples of this in the digital fabrication space, using simple things like a Monte Carlo Markov chain to build an electrical mechanical device, using simulated annealing to build different types of metamaterials, using iterative neighborhood search to build different types of casts. And all of these different tools are using some type of iterative process that kind of flows like this. The designer inputs a set of existing designs, and then they evaluate them based off of their objective function. They then choose a design from that set of designs and consider whether or not they want to accept it or they want to continue iterating. They then modify the design, which produces something new in the design space, and they reevaluate it. And then they repeat this process over and over again until they eventually find a design that meets their acceptance criteria. In some cases, that's going to be the global optimum. Much more often, it's going to be something that satisfies their set of requirements. So it could be somewhere scattered in the space, but it's not going to be one of those poor performing designs. With Optimum, we break up this existing iterative process into components from two different libraries. The first library is a domain agnostic library, which should work for a variety of meta-heuristic methods. And then the second one is a domain-specific library, which is made by a programmer paired with a domain expert who has the kind of domain expertise to guide the search process. So from that domain-specific library, we could develop a customizable objective function. And then we use a domain agnostic design selection strategy, followed by a stopping criteria that is domain agnostic. And then we break up modification into two separate steps. The first one is choosing a modification from a set of modifications available. And the second one is applying that modification to create the new design. Choosing a modification can be done domain agnostically, while applying the modifications to come from that domain-specific library. I want to talk first about how we build that domain-specific library using that programmer and the domain expert together. This is a type of heuristic-based search, and so we break up the idea of heuristics into two components. The first one are objectives, and these establish different design goals. These are how we build a customized objective function. Objectives are a function that take in a design and will return a value between 0 and 1, where 1 means it's meeting the requirement. We then have modifiers, which make small changes to an existing design. So this is a function that takes in a design and produces some new design in the space. And then these fit into this iterative process here, so we can kind of plug and play with different objectives and modifiers for the library. We then ask domain experts to organize their objectives and modifiers to create a search query. They first provide a set of weighted objectives, and we have an objective function, which is just the weighted sum of these different objectives. This lets them to kind of rank in priorities of different design goals and establish how important they are to the final result. And this can be customized by the end user as well as the domain expert. We then ask them to provide a set of modifiers and a weighting between objectives and modifiers, which specifies how the domain expert thinks different modifiers will do in improving different objectives independent of each other. And these weights are considered the heuristic weight and establish that priority. Looking at a few of the domains that I've worked with at Optimum in, we can think about how domain experts go through this process of defining objectives and modifiers. So for example, in the space of occupational therapy, they might use existing standardized parameterized designs for creating 3D printed splints. Then they have to go through the process of tuning all these parameters to fit to a particular person, as well as meeting different types of clinical requirements. So for example, they might be concerned with thumb flexibility, which is affected by parameters that you modify on this axis, or wrist flexibility, which is modified by a different set of related parameters. They care about comfort features like breathability, which is affected by the density of the holes poked into the material. And then finally, they care about another set of parameters relating to fit to the user so that this will snugly attach to the person's body. In the knitting space, we can use the knowledge from craftspeople to think differently about solving problems. So for instance, they can come up with a variety of physical properties for objectives, and then they can come up with a variety of modifiers for changing these textures so that we can do kind of a program synthesis process, creating the original NISBEAK files. So for example, if we want to use that estimation of curl I talked about earlier, we can build an objective function which has a set target curl, and as it approaches the target curl, we increase our value to 1. Relatedly, we can have a modifier which just switches a random direction that a loop is pulled through another loop, and this is going to ultimately change that function for the subgraph so that you can affect curl. Our most recent work with Optimum has been in the space of designing tactile maps for people who are blind and have no vision to help them navigate a new space. Here we're thinking about the disabled person as a domain expert because they have a lot of knowledge about what are their different goals in navigating a space, as well as what are their preferences for how that representation of the space can be done. We've done a study of using Optimum with a set of 6 blind and low vision users, and we compared the designs to standardized maps, which they could not customize for the same space, and customized maps where they created the map entirely on their own. They had to set the different weights on objectives and modifiers over a Google form, and they only got to do this once without any guidance. And despite that, the optimized maps were actually more successful than the customized or the standardized maps, partially because the optimizer could just go through thousands of iterations in the time that it would take an individual to do one. And so they were much more likely to kind of get through to the design that they needed. In order to build these heuristic maps, Optimum, once you give it your library of objectives and modifiers, will automatically generate a GUI for you so that you can set these different weights, as well as relating different objectives to modifiers and changing their parameters. And if building heuristic weights on your own seems like too tedious of a task, we also built an automatic tuning algorithm for learning those heuristic weights. This follows a Bayesian model where we assume that the weights are just the probability of improving each objective given each other modifier. And we generate a set of different designs by applying modifiers in a kind of cyclical process. When we can look at heuristic weights in a variety of the domains that we've worked in, we found that the designs that used either domain expertise, either from the automatically generated weights or from a domain expert, outperformed the ones that used uniform weights, where we just set this value to 1 for every modifier and objective. We also found that there was a lot more randomness, which would be expected in having these kind of uniform weights. This is just a random walk through the design space. And so what we're showing here is that the domain experts are really able to embed the expertise needed to find the high quality regions of the search space. However, to do this, they also need those domain agnostic strategies that I wanted to talk about. So if we just apply the same modifier or set of modifiers over and over and over again, we're doing some kind of basic hill climbing process, which is fine, but it will often not reach a global optimum or even a design that satisfies a user's requirements. However, we can build on the idea of heuristic optimization with meta-heuristics, which are strategies for applying these different modifiers and objectives in specific iterations. Just like we broke up heuristics into objectives and modifiers, we break up meta-heuristics into design selection and modifier selection. The design selector is going to go into this component where we select the design given the objective evaluation, and then modifier selectors are going to be used to choose which modification to apply in each iteration. So if we want to look back at that heuristic map that is applied, that is given to the system by the domain expert, we can use the objective function to figure out which designs to select in each iteration. Now, generally, we could choose a design randomly, completely ignoring the objective function, or we could always choose the best design. But often we need to do something in between the two, where we maybe statically set a random acceptance of the higher quality design, or in the case of methods like simulated annealing, we want to set that entropy function based off of the amount of time we've been iterating or some other component of the optimization. And so we're able to build up a library of design selectors that are parameterized along this spec. We then want to look at the heuristic weights and use them to kind of figure out how to select a modification of each iteration. We've developed a expected improvement score for how much we think, based off of those heuristic weights, a modifier is going to improve an objective function given the set of objectives and their current scores. And just like design selection, we can kind of frame this as a spectrum between choosing a random modifier in each time or choosing the expected best modifier. We also have other spectrums that we included, such as best neighbor, where we apply all the modifiers and then look at the resulting scores, or looking at the history of improvement rather than using the heuristic weights. And so you have a lot of different ways of kind of looking at different quality functions for modification. We also have a GUI for mixing and matching these. And because design selection and modification selection are independent from one another, the domain expert can actually rapidly test out a few different of these components without understanding the underlying optimization process. So for example, we go through this stage for building all of the different tools I've been demonstrating. In the space of knitting, we ended up on something that's very similar to simulated annealing, where we use that kind of entropy function for design selection. And then we use expected improvement for modification. We can also do things like ant colony optimization, where we just choose the best design in each iteration, and then we use a history of improvement to apply the modifier. We use the best design and then penalize penalize modifiers that have declined the objective function in the past. That gives you something like taboo search. You can choose a random design and use the expected improvement. That'll give you something like a Monte Carlo method. And then you can choose a random design and then choose the best neighbor, and that's going to give you something like variable neighborhood search. And we can kind of go on and on about applying all of these different components to create classic meta-heuristic methods, as well as developing new ones that work well in a new space. My goal with Optimum is to support rapidly building and prototyping generative design tools in a variety of domain-specific spaces, particularly ones where the domain experts can define a set of heuristics. I think optimization that supports bringing those domain experts in is really important because it needs to build on domain-specific concepts in some way to get through the search process. And it's often very rare to find someone who both knows how to write an optimization system, as well as someone who has a domain expertise. We structure the system around a variety of pluggable mix and match components because this really limits the points of failure in building the system and makes it much more likely that you're just going to get to something that satisfies your needs over a quick set of iterations, rather than having to build it from scratch and often reach a failure point. And then finally, we provide a set of automatically generated GUIs because we want the domain expert to really be a first-class citizen in the development process. We don't want them to be completely reliant on the programmer to explain what's happening in the optimization and the different design decisions that are made along the way. I think that including these domain experts in the optimization process will ultimately increase our access to these domain-specific tools. It'll make it easier to find teams that can work together to build these. Of course, I think there's still a lot of work that needs to be done to support both generative design and the other types of digital fabrication tools I've talked about in the medical space. I talked about a set of limitations at the beginning, thinking about things like deformable material design. And to start solving some of those problems, I've built a pipeline for knit programming so that we can really explore this new space of deformable materials and think about the types of challenges that these communities encounter when using those tools. I also am worried about design reuse, making sure that these different resources we have online are made widely accessible and can be reused in an effective way. And so to do that, I've built a system that supports model reuse and expands the collaborative design resources by applying software engineering principles. And then finally, I'm still interested in this really small design time that clinicians are interested in, something that can fit into a single patient appointment. In order to do that, we need automatic domain-specific customization. And I think that can be driven by domain experts building optimization tools for themselves. Right now, they require a programmer, but I think there's a lot of challenges remaining in trying to remove the programmer from as many steps in the design process as possible. There are also a variety of other unsolved problems in the space of medical making. We want to continue working this body compliant design tool chain and expanding beyond knitted textiles to other types of materials. We want to support collaborative point of care, really thinking about patients as a designer in this process so they can work alongside their clinician. And there's many challenges that remain in terms of verification and safety of efficacy of these designs. How do we know, looking at a new design, if it's going to be safe? What about how we change it? How do we know that that change is going to meet some set of safety requirements? I've talked a lot today about my role in kind of bringing this space into healthcare, but it would behoove me to not really talk about some of my interests in the space of disability theory and how it intersects with digital fabrication. Disability theory is a type of critical theory which really thinks about reframing who we see as experts in a new problem. It focuses on people from marginalized identities, or people with disabilities, or the caregivers who surround those different communities. And I really think that this is an interesting approach to take because it thinks of them as innovators and allows us to collate new expertise from communities we might otherwise overlook. I also am really interested in building tools that serve these communities, really focusing on applications in marginalized communities where we can have the most impact. But that said, there are other spaces beyond healthcare that I want to continue to push into. I'm particularly excited about working on accessible fabrication, including people with disabilities who do not have access to these tools right now, in the process of creating new tools. I also want to learn from the success we've had in the PPE crisis during COVID-19 about how we can use fabrication to support just-in-time localized manufacturing rather than relying on a global manufacturing system that often fails marginalized communities and is not very robust in a crisis. And then finally, I think we need to expand fabrication work into the space of sustainability. In particular, textile design for the garment industry is one of the major polluters globally. And part of this is because they don't have the tools to actually make these materials without wasting a lot of material in the process. So building up new design tools that really take this as a first priority might actually change how much waste we have in manufacturing these goods. As always, my research kind of ties back to that promise of digital fabrication that lured me in the first place, the idea that anyone could make just about anything. I want everyone to be able to make anything, but in particular, I want to help the communities that have been traditionally excluded from manufacturing and digital fabrication in bringing their unique set of knowledge and expertise into the fabrication space. My approach to digital fabrication research comes from these perspectives of these orthogonal experts, and I've been able to have a really critical impact in those communities by looking at their orthogonal expertise rather than trying to impart my own technologies into their space. I'm excited to expand in these spaces, but I'm actually more interested in talking to students and working with students who come from different types of backgrounds and can connect with new types of orthogonal experts to find the problems that best fit with the technologies we have and prompt new interesting problems for us to solve. And with that, I really like to open it up for questions and a discussion of this work. If folks are in the Zoom call, I'm happy to see things over chat, or I think you can speak up and we will hear you in the classroom. And for folks in the classroom, remind me to revoice your questions. Yes.
So I enjoy how you are bringing a lot of principles of software engineering to the end users who are not necessarily. So my question is more like, towards your second part of designing. How can we use design principles of software engineering to make our designs more extensible, more ignorable, more maintainable by others? So working with edge users, there are lots of things that we as professional software engineers, computer science, we appreciate abstraction, specifically that's how we do complexity and conservation. Have you seen that the end users are pushing back when you're saying, you need something that we can modularize, we can encapsulate, it helps us to reuse, we can encapsulate this in a routine and we can use it? Do you see them having like a pushback and say, yeah, I can see that you could do that, but I like to do things the old way? Or do you see any pushback from end users to adopt these principles that we adopt as a abstraction and encapsulation modularity? So I'm curious to see what do you see in that space.
Yeah, so for the folks on the Zoom, the summary of the question is, particularly in that system where we use software engineering principles and 3D modeling, did we see any pushback from the users that they didn't necessarily want to apply those principles?
Yeah.
So this is actually kind of an interesting thing in the user study. There was another workshop that I didn't have time to talk about today where we did kind of a more free-form activity where they used the tool. And some of the kind of responses we got out of those folks was that they weren't necessarily thinking about it as software engineering, but they were using it from other design practices, and they were actually excited to see it in the tool. So the example they gave was, we were working with a set of artists who had some familiarity with tools like Photoshop, where they're really accustomed to using different layers to abstract the different processes that they're applying to an image. And there was some kind of quote along the lines of like, this is like layers in 3D modeling, which is not at all how we had designed it. But I think there are lots of communities that develop their own set of abstractions in their practice. And then the tools that they have don't use those abstractions. And so having this more flexible system where they could define those abstractions for themselves was really effective. We also built so we provided a set of simple programs you could attach to geometry, but it was also an extendable system that just uses Python programs. And so in the case, it's you know, you don't necessarily need to be a computer scientist to work with a basic Python function. And so a lot of the folks were interested in taking the system and writing their own code, learning the code, just enough to do simple activities. And so I think there's like a marriage in that way of there are enough folks who use this kind of 3D modeling platform who are going to adopt some of these principles in a way that they can apply in these kind of systems. Yeah.
How do you do this? The reason I'm asking is there a bias in that? They might set that they're interested in.
Yeah.
At the end of the day, you want to just one.
Exactly. So I have a bunch of different strategies related to projects. For the Zoom call, the question was essentially, you know, how do I select these users and does that introduce bias into these studies? The truth is there are always biases introduced in the selection process, even if it's just kind of like a local sampling. And it depends on the type of study. So the community we worked with for the software engineering project was a makerspace in Honolulu because I was living there at the time. And so that was just kind of the community we had access to. The nice thing about that being a public makerspace is we had a really good smattering of gender, of race, of looking at different kinds of educational backgrounds and different professions. So we had people who were not professional 3D modelers, but did engineering work or did professional design work. And we had people who were like high school students who had no experience, no practical experience. In the medical space, a lot of this is like communities of opportunity. So Make for COVID, for example, was like, I happened to know someone who was there and I gave them a call and they said, come on in. And that does introduce a lot of bias. I would never claim that Make for COVID was like other communities because, well, for one, we've actually looked at other communities and we know that they were completely different. But also just because like it's a very specific setting, right? They were influenced by the state that Colorado was in, which was different than like the Eastern Seaboard. So a lot of the methodologies that I adopt from critical theory and anthropology when I'm doing this kind of longitudinal work are focused on less on using, trying to generalize this knowledge, but instead on trying to kind of pinpoint how these biases are interplaying with different systems and trying to think about, what did I learn here? Let's go try to find that theoretical framework in other places. And so you don't necessarily look at the original community and say, this knowledge I gained will generalize. You say, this is a theoretical framework, which others can then take to other places and look for that generality over time. Yeah.
So I wanted to ask, how do you know when a design is a good one? Meaning that you kind of implement the fabric and you give it to the user to test it, and you go back to the tool and remodify it, or just do it again and test it after?
Yeah. So the question is, you know, how do you kind of make the decision when to stop the iterative process? Are you talking about an optimum where we have the two? Great. So those iterations are actually happening many times a second. So they're never going back out to the user. It's just going back into the objective function. I didn't have time to talk about it in this talk, but we have stopping criteria and a library of stopping criteria, which are just based off of common patterns in optimization. So we'll do things like the user can set a threshold score and it will just stop when it reaches that score. You can do things like, you know, run until you run out of iterations, or you exhaust some other resource in the design process, and then it will return it to the user. So here, the design process for the person is more tweaking the objectives to get the result that they want, and then rerunning the optimization to see if that gives them the correct result. In all of the studies we've done so far, we have, because of time restraints, limited users' access to that part of the iterative cycle. They couldn't go back and change their objectives. And so we were just evaluating their like first go at the system. I think if you were using this in a real design environment, like if we were to bring this into a clinical space again, people would spend a lot more time kind of tweaking things, learning how different objectives affect other things, and how to find the correct regions of the search space. So it's a design process that we're not really fully aware of yet.
Any adaptation being needed to create heuristic maps that consider more than one domain expert? So, like, for example, with the split into the occupational therapist expert, or if you consider former patients who would consider also.
Oh, that's a really interesting idea. We have really been thinking about. So the question is, in particular for Optimum, if we had thought about kind of teams of many different types of domain experts using the system together, or at least using the same system rather than just one domain expert every time. We hadn't thought about that yet, but it's a really interesting idea. And I think that kind of flexibility is part of the reason that we wanted it to generate a user interface. So we don't provide it just one heuristic map and that is forever what it is going to generate. You can modify that heuristic map. So you'd have to have the programmer to add to the library and create new objectives and new modifiers. But if you want to just try out different relationships between those objective and modifiers, you can do that really easily. And so the idea here is that, you know, maybe we had been thinking like an occupational therapist help builds a tool and then they share it with other occupational therapists, but you could maybe apply it to, you know, someone comes up with an objective function that was provided by their clinician, and then they say, oh, I actually want it to fit a little bit differently, or this is not comfortable, maybe they can tweak it in some way. I think the system's flexible for that, but we'd still hit this kind of challenge of if they have some new modification strategy or objective that they care about, that's not in the system, how do they then get it into the system? And in order to do that, we're going to need to remove more of the programming aspects of the toolkit. That's a great question, thank you.
So yeah, my question is, so regarding this optimization that you are doing, and I think it's also related to the question you asked. So you have this cost function, but you don't know the cost is the correct cost in the sense that what comes out of the, let's say, the local or the global optimum is actually what the user is going to like. For example, in the case of the thumb split, so we don't know if that's a good one, right?
Yeah.
Even though if the optimization is doing the job. So how does it work? Because you print it and then the user is going to use it, and it takes a few months, or I don't know, there's a lag till from the time that the user is going to use it till the time that the user is going to decide, oh, this is not a good design, right? Because I don't see the improvements I'm supposed to see. So is there a way then implementing it in real life, doing also this testing in the simulation environment? I don't know if that's even doable.
Yeah.
That's what we do in, let's say, in self-driving car.
Yeah.
We don't immediately deploy on the road. We do simulation, right? It's called hardware in the loop simulation. And then we run months and months of simulation until we converge to something that we think, okay, this seems reasonable. So now let's deploy it, right?
Yeah.
So I don't know if there is a simulation environment for this type of case studies.
Not yet, but so the question is what happens if, particularly in a domain like the splints, where you're going to be using it over a period of time and you might find out like a month later, it didn't work. This type of optimization method is really not tuned for something like that, but more like looking at Bayesian optimization methods might actually work, where we're thinking we don't actually know what the objective function is. We can kind of take a guess at it. We can have some human evaluator or some very slow process, like a much more extensive simulation process, figure that out. But we still, you know, now we're talking about iterative cycles in the system that may take a few minutes or hours or a day or a month if it's a human evaluator. So there are lots of methods out there for kind of adapting the optimization process as this feedback is rolling in. And particularly, I think there was a really good toolkit that came out of Google called Google Visor that looked at this, where they were, one of their exciting demos was like learning cookie recipes, where they had different Googlers eating the cookies and then evaluating, is this a good cookie or not? And then they had to kind of take that feedback in. So I think that there are ways of adopting those methods into a system like this, where we're kind of then iterating. Now there's, in the clinical space, there's a real cost here of a clinician really doesn't want to hand something out that they're being told like, oh, we're going to fix it in a month. It's not quite right. They're like, well, this could do a lot of harm. Maybe that won't do too much harm if it's a splint. Could do a lot of harm if it's like something you stick inside your body, because you're not going to take that out. And so in those cases, we need to kind of defer to the domain experts to figure out, can we do enough experiments in advance to know what's generally going to work? Can we come up with a kind of restricted set of objective functions that we know results in good quality products. And in that case, you kind of need to go through the same review processes in standard medical devices. You do need to go for these algorithms.
You got it.
Oh, yes. Oh, tiny chat screen, so I'm having trouble reading it. There we go. Looks like Clinton says, in one of your papers on medical making, you report some interesting issues in the use of social media platforms for supporting making. Do you have a take on what kinds of platforms may better support making going forward? So the paper that Clayton's referring to was an analysis we did at the beginning of the COVID-19 pandemic of the kind of like communities that were on Facebook and Reddit and other places who were doing this medical making work. And the discourse was toxic. I got a few death threats in the process of working with those communities. It was an accomplishment, I guess, as a researcher. It was my first dabble into social media. So some of my thoughts on these different platforms, I think, particularly in the clinical space, the NIH is probably just a better platform because it's carrying a lot of the norms from the clinical community. It has the dressings of a formal review process. It's peer reviewed. It's going to be attractive to kind of institutional communities who are going to be sharing a lot of the same values as the end users. For wider maker communities, and we do want a wider group of people to kind of adopt these technologies and come up with creative solutions in it. I think the best thing is to use platforms that are very flexible for creating small communities rather than these really large global communities. So places like Reddit tend to be very successful because you usually have like a small group on a particular forum, as opposed to Facebook, where people were making these, like, I think one group ended up being over 100,000 people, and Facebook was, kind of had a black box way of deciding which posts got put up on each person's screen. So everyone had missing pieces of information, and they get frustrated and they feel like they're doing really important work, and someone else is critiquing that, but they don't have missing information. And then that creates a very vicious cycle. So in this space, I'd actually say to build the platforms for maker communities, we need to kind of step back from the technology. We need to support just small communities. It needs to be maybe more local or more specific to something, and it shouldn't have an algorithm kind of, at least none of the algorithms we have in the loop making decisions about who sees what when. I think are we at 4:30? Should we?
Yeah. So is there any other question? Okay, thanks to the speaker.
This is the most crowded classroom I've watched.